Hello everyone, my name is Joshua McDonald, and today we're going to be talking about displays and display technology. So, displays are everywhere. We have them in our homes as our TVs. We have them in our pockets with our phones. We have them on our wrists with our watches. We have them in our cars now, and some people are crazy enough to have them on their mirrors. Displays are everywhere. But how did we get to this point? How do we how can we make displays as small as they are but also as big as they are? What is the history behind displays and how did we get to this point? That's what we'll be talking about today. Displays and the technology that supports it. So one of the first types of displays that's still somewhat used today is the vacuum fluorescent display. It's pretty much a display where you really all you want to display are numbers, or if something's on or off. And that's because of the technology and how it's cheaper to produce it this way. So you'll generally see these types of technology or these types of displays in your car, on your older radios, and in fact, some of these displays were used in the Apollo missions. The display that you see on the right is a recreation of one of the displays from the Apollo missions recreated with a 3D printer. So how does this type of display work? Well, we have these sort of small elements which are comprised of a cathode, an anode, and some sort of filament. And they're laid out in this sort of pattern or whatever pattern someone wishes. And what we do is we send an electron across the filament, or a current across the filament, in order for it to fluoresce and illuminate. And we can specify specific regions on these patterns to put a current through, and from that we can create a number or an image. In this case, we're creating a 5. You can see on my microwave at my home, I have one of these types of displays, and all it does is it shows the time of what time it is here on Earth, or how long is left to cook the microwave. And you'll also notice that there's things like demo and other smaller patterns along the edge, and those are simply turned on or off. Now, these are basic images, and most of the time we just display numbers, like I said. But what happens if we want to display something more complex? Well, this is where the invention of the cathode ray tube comes in. But before we can talk about the cathode ray tube, we need to talk about light bulbs. Light bulbs are one of the easiest way for us to produce light, and when it produces a photon, or ray of light, it just kind of leaves from the source. And if we generated another photon, you'll see that it kind of does the same thing, and it'll do this over and over again. Now, this is just one of the possible photons or beams of light that come out, and if you've ever seen a light bulb turned on, you'll know that it fills all around. And since it fills just a huge space, we can't exactly get an image out of that. So we have to do something to modify the direction a photon will move. And that's where the cathode ray tube comes in. So we have our cathode and our anode. The photon will travel from the cathode to the anodes, and these coils right here will induce a magnetic field across the tube, which will deflect the photon onto a fluorescent screen, where the fluorescent screen will absorb the electron, just like the filament, and produce a pixel. And with this tube, we can create a magnetic field which allows us to move a photon up, a photon down, left, or right. And from this, we can start to generate an image. And that's how some of the first TVs were actually made, with cathode ray tubes, where they would scan photons across the entire display, deciding where there would be a pixel and where there wouldn't be a pixel. And this technology was still common into the early 2000s. In fact, the first possible change in technology, the plasma TV, didn't really become available until 1997. So these guys over here on the right were still being used in the early 2000s. In fact, some of the earliest TVs that I watched movies and my cartoons on were on one of these giant cathode ray tubes. But one of the biggest downsides of this is how thick these TVs are. It wasn't uncommon for one of these TVs to be about the size and weight of a child. And trying to move one of these was not easy. So engineers decided to figure out a new way to create a display that could be thinner than anything else before. The LCD, or the liquid crystal display. These displays use a stack up of multiple films and multiple aspects in order to produce the images that we're used to today. So what happens, if we follow this GIF on the left, is an LED, or a row of LEDs, or a filament lamp, will shine light into a light guide plate, where the plate will take out a small bit of light as it goes up the plate until at the very top all the light is sent through to evenly send light across the entire image. From there, it goes through this liquid crystal display, or this liquid crystal layer, which allows us to change the crystal structure, allowing us to change certain aspects of the image. They'll then go through a color filter and out into an image. So when we talk about rearranging this crystal, what do we mean by that, and how does this affect the picture? Well, this animation here will hopefully explain that. So if we send an current through this crystal, we can decide to either keep it in its normal state, where all the light will pass through, modify it to maybe half, so that way only half the light goes through, or rearrange the crystals so that all the light is blocked. Now, this isn't exactly how the crystals move, but the idea is still the same. We can, depending on the amount of current that we pass through these crystals, we can either have a fully on pixel or a fully off pixel, or somewhere in between. And when we do a RGB stack up of this, we can start seeing full color pictures. Now, let's look at what this sort of looks like as we zoom in on, just a TV that I have laying around outside. So what I'm doing here is I'm setting it up and putting in a special little card that I have from the OSC that has this small little lens in it. From there, I can see the small color filters that create the yellow color. And since it's yellow, you'll only see the red and the green coming through. But if it was white, you would see that full red, green, and blue. So a lot of people have been figuring out ways to make the LCD thinner because there's a certain limit to how bright you can make a filament in order, or a backlight, and still get the same resolving power or the same number of pixels and get uniform brightness over the entire image. So a new technology has sort of popped up, the OLED. The OLED is an organic LED technology. So what does that mean? Well, if we look at this animation here, we still have our cathode and our anode, but instead of having just a normal filament, we have an organic filament. And as we pass a current through this organic filament, we can get our different red, green, and blue colors. So what we can do is we can take an array of these red, green, and blue OLEDs and use that to construct our images similar to the LCDs. Now in this video, I took a recording of my cell phone, which is a Samsung S9 Plus, which uses a OLED technology. And you'll see by the pattern, or see that it does the same thing, but the pattern is a little bit different. Sorry for the shaky camera. I was having trouble trying to hold the card and not actually touch my phone and move it to the next screen. So with this, you'll see that there's this sort of diamond pattern through the display. And that's because each individual organic component has its own smaller pixel, and it's a more compact way to get a higher density of pixels than with an LCD. And that's because we generally have our phones closer to our face than we do our TVs. And it's just another way that we can spread out the color filter in order to get all of our pixels. Now, there are other technologies which could become thinner. The main problem with OLEDs is the fact that we have to use an organic compound. While it's advantageous that OLEDs are more flexible than our traditional LCDs because we don't need a rigid backlight or a rigid diffuse plate, the downside is the organic components, which tend to burn out in comparison to other metallic filaments. So another new technology that's sort of in development compared to being used commonplace is micro LEDs. And the name kind of explains it all. It's a bunch of LEDs that are micro. And as you can see from this image here, our normal LCD has all of these stacks, which makes it thicker. The OLED, it's better, it's thinner, but the micro LED, even from there, is much thinner than the OLED. And since it uses metallic components, we don't have to worry about the organic layers burning out over time. So with micro LEDs, we use the same technology of normal LEDs. And with LEDs, it is a semiconductor where we take our cathode and our anode, and when we send an electron across it, we can actually generate a photon or a piece of light. And depending on the amount of energy that we send across, we can create different wavelengths of light. Now, this may not make too much sense, so I've got a demonstration here in relationship to walking downstairs. So, as we walk downstairs normally, one step at a time, it doesn't have a lot of energy to it. It doesn't take a lot of energy when we land, and we also don't have to worry about all the energy going into our bodies. It's plus it's really safe to go down one step at a time, but it's not the fastest way to go downstairs or the most efficient way to go downstairs. Now, let's talk about going down 2 steps at a time. Going down 2 steps at a time is, it requires a lot more energy to do, but at the same time, it is a lot faster. And it's still relatively safe. Now, if we decide to go down 3 steps at a time, you can see that the energy that I'm feeling as I go down each set of stairs is a lot more than when I was going down 2 steps at a time, and is a lot more dangerous than going down 2 steps at a time. So you can kind of imagine the generation of different wavelengths of light through the semiconductors like that. Engineers will generally design their semiconductors, their LEDs, to go down 2 steps at a time, or some smaller subset of 2 stairs, in order to generate the red, green, and blue that we see, but won't design it in such a way that we have drops of 3 steps at a time, which could create harmful X-ray or gamma rays. Now, one last technology that's on its way into our phones and into our displays here in the hopeful future are quantum dots. So far, quantum dots are already being used as filters for light, and that's because we can produce them a lot smaller and a lot more efficiently than with small films like we use with the LCDs. And there are companies that are working on ways to make the quantum dots themselves illuminate the light themselves. So, similar to everything we've been talking about, we send a current across the quantum dot, and it'll create a red, a green, or a blue pixel. And this should be our theoretical thinnest display, but still have all of the advantages of our flexible OLED displays, and but also be as efficient as our micro LEDs, because the quantum dots are smaller, and we can arrange them in a pattern such that they're more flexible. Now, I didn't talk about this before, but the displays that we use now have polarizers in them. And what is a polarizer, or what is polarization? Well, if you want to learn more about that, there's an awesome video about that on our website. So I'll go ahead and give you a second to go watch that, or you can go ahead and watch that after this video. But what's important for displays is that the way the stack-up works, unless we include a polarizer at the end, we get some funny-looking pictures, or we don't see the picture at all. So we see with this display, outside of the polarizer, the film that he put in, we can't see the image whatsoever. And depending on the orientation of that polarizer, changes if we can actually see the picture in its normal view or a sort of inverted view. And what's really cool, and he'll show this here in a second, is that when you pull a set of glasses with it, your normal polarized sunglasses, the same thing works. So if you've ever had glare or couldn't really see your displays if you're wearing polarized glasses, that's the reason why. But a cool trick is you can include a polarizer in front of your display in order to create, as this video up here shows, a DIY privacy monitor. So that way you can keep all of your work private. So, I'm sorry there's no real demo, but creating things like quantum dots and LCDs and that sort of thing is a lot more complicated than bending light. So there's no fun activity for you to do at home, but if you have any questions, feel free to put them down in the comment section below, and I or one of the other engineers here at the Wine College of Optical Sciences will be glad to answer them. Thank you for your time, and have a great rest of your day.